Hi, I'm Alexander Vakhitov, and I'd like to present our work on uncertainty-aware camera pose estimation from points and lines together with Luis Ferres-Colomina, Antonio Anguda, and Francesc Marennoguer. We follow well-known ColMap and ORB-SLAM systems and consider a pipeline for camera pose estimation consisting of four main steps. It starts with a minimal P3P solver inside and runs a loop. Then the pose hypothesis is used to define a consensus set of features. The consensus is processed with a PNP solver to obtain a better pose hypothesis. Then we find a better consensus set. Finally, a fourth optional step is to optimize reprojection cost over the consensus set. Historically, camera pose estimation algorithms were used for images of objects with known, perfectly accurate CAD-like models. However, nowadays we often use maps built using structure from motion or visual SLAM techniques, where accuracy changes significantly from point to point because of feature detection inaccuracy and the triangulation errors growing quadratically with point camera distance. We assume that a 3D point X is projected onto the 2D point U on the image plane. The 3D point covariance matrix sigma X and the 2D point detection covariance matrix sigma U are known. The line segment is represented using its 3D endpoints P and Q with corresponding covariance matrices. The line segment projection is defined as a 2D line equation with known variance of line point distance measured in the image plane. In this work, we present algorithms for camera pose estimation from 2D-3D feature correspondences, where both 2D feature detections and 3D feature locations are assumed to have different uncertainty given in the form of covariance matrices. Our methods can use only point or point plus line feature sets, while before only 2D uncertainty was considered, just for points. We generalize the EPNP method to the fully uncertain setting. EPNP solves a least squares problem. To estimate covariances of the residuals, we require 3D covariances in the camera frame. We assume either isotropic covariance or a known rough rotation hypothesis. Finally, we solve a weighted least squares problem. We also obtain a generalization of the DLS solver in the paper. Typically, the pose is refined using nonlinear optimization, minimizing the reprojection residuals. The residual covariance in our setup depends on the camera pose, while in a standard situation it is assumed constant. We propose to do a Gauss-Newton step as though the residual covariance was constant, and then update the estimate of the residual covariance. We show that the proposed procedure is fast and accurate. In the synthetic experiments, we justify that the proposed pose solvers match the accuracy of previously published uncertainty-aware methods in the case of 2D noise and achieve state-of-the-art in the general case of both 3D and 2D noises. Here we show the weight associated with each point inside our EPNPU solver. We see that although further points tend to have lower weights, still weights of the points at the same depth can differ substantially. This video shows the ground truth camera pose and inlier set in blue, the pose and inlier set estimated by EPNPU with standard refinement in green, and the pose estimated by the proposed EPNPU with uncertain refinement in red. While in easy cases the methods perform similarly, in difficult situations the proposed solver tends to have better accuracy. The cumulative distribution functions for the real experiments on the Kitty dataset show that the proposed EPNPU method is the most accurate, and the proposed DLSU solver outperforms the original DLS solver. So, same holds for the 2MARGBD dataset as shown in the paper. The error histograms show that in average case the proposed EPNPU tends to have lower errors than EPNP or 2D uncertainty-aware CVPR. The same holds for the line features, where the EPNPLU method is more accurate than the other methods. Here are the references. To conclude, in this work we have generalized the EPNP and DLS methods to a fully uncertain setup with uncertainty both in feature detections and in their allocations. We proposed a new uncertain pose refinement scheme. Both solvers and the new refinement scheme contribute to the increasing accuracy of camera pose estimation according to synthetic and real experiments on two datasets. We share the code at the link shown.